Kids, it's Matt here. I want to talk to you for a few minutes about entropy. This is going to be the beginning of chapter 17. We've got chapter 17. This is Thermo 2. And before we get into Thermo 2, I'd really like to explain what it is we're looking at. If we look at a regular reaction grid where we have reactants over here and products over there, what we really would like people to understand is that the outsides of this graph, here and here, this region and these regions, that region in itself, both of those areas are thermodynamic. That's thermodynamically controlled. That means delta H, delta S, delta G. This middle area in between, this is where rates come into play. This is kinetics, and that shouldn't come as any surprise when we talk about catalysts lowering activation energy and doing that. And so we're dealing with things just looking at a snapshot of those reactants and those products and what that really means. Now, Thermo 2 starts out talking about spontaneity. Spontaneous reactions. Spontaneous reactions are reactions which will occur without any outside intervention. Most books talk about rust, oxidation of iron. If we take iron and we expose iron to oxygen, we're going to get some form. And we're going to need 2 of those and 4 of those. This is going to be spontaneous. And if we talk about the reactants, from the reactants to the products, things are going to happen normally by themselves on their own. But in the middle, the thermodynamic control, this is going to be a very slow reaction. It's going to happen. It's going to take a long time. It's not going to happen overnight very quickly. So that's spontaneous. When we think about non-spontaneous, let's take something like a combustion reaction. And we add that and we get CO2 and we get H2O. And we could go through and balance. I don't want to spend the time doing that here. But this is going to be non-spontaneous. And the reason I know that is because this is methane gas. It just doesn't spontaneously combust by itself. We have to put activation energy into it to get it over that thermodynamic hump. So by itself, it could happen, all right, spontaneously? Probably not. We have to light it. We have to have an ignition source to make this happen. So this chapter is all about spontaneity. Now, spontaneity is determined by delta G. And I want to make sure your book starts out in a little bit different fashion, but for our purposes, delta G is called Gibbs's free energy. And Willard Hosea Gibbs, there's a nice statue of him up at Yale if you ever go visit outside of the chemistry building. There's a statue of Gibbs. Basically what that means is that is the energy available to perform work. So if negative delta G, this is going to be a spontaneous reaction. If we have a positive delta G, that means it's non-spontaneous. And that doesn't make very much sense to us until we start looking at the system versus the surroundings. In the first situation where G is negative, if G is negative, then the system is giving off energy. That energy is going to be available to do work. In the second one, where G is positive, now we've got putting energy into that to make it work. Well, what's delta G equal to? There's got to be a calculation base here, right? No problem. This we're going to spend a lot of time with in our next video, but this is delta G equals delta H minus T delta S. Well, we already know what H is. We already know what T is. T is going to be in kelvins, by the way. But delta S and delta G we just defined. Delta S is our next friend that we have to define here. Delta S is entropy. Entropy is just a measure of disorder in a system. And so in our case, that disorder can take on two different ways of looking at this. Your book talks a lot about microstates. Microstates are just the number of arrangements that molecules can have. And so microstates are particle arrangements. So if we look at, let's go back to, no, let's take that iron, I'm sorry. That was the wrong reaction. I wanted the iron plus the oxygen to make two Fe2O3s. Iron is a solid, oxygen is a gas, and Fe2O3 is a solid. So we can look at microstates and particle arrangements in two different ways. We can look at things that are called positional entropy. And what that's going to do is talk about states of matter. So we want to look at our iron reaction here and say, well, what's going on with the states of matter? We're going from a solid and a gas to a solid. This is becoming more ordered as we proceed from left to right. So what we would say is delta S is decreasing. We're decreasing. We're decreasing the amount of entropy in this system, how much disorder there is. So we can look at it in terms of states of matter. And as far as entropy goes, pardon me, if we go back, delta S of a solid is less than delta S of a liquid, which is less than delta S of an aqueous, which is less than delta S of a gas. Gases have very high disorder, and solids have very high order, very low disorder. So we can look at it in terms of states of matter, and that's fairly important to make note of. But then the other thing to make note of about positional entropy are the number of particles. Particles and positional. In our case, we had 4 irons, we had 3 oxygens, we had 2 Fe2O3s. So in this case, we have what looks like 7 particles, 4 and 3. 7 is greater than 2, therefore delta S should be negative. This is a brief overview of positional entropy and thermodynamics. In our next one, we're going to talk about free energy and how we go about calculating that. In the meantime, I'm Smath. I hope this helped you.